Here we consider how the spring mass system would be affected if we externally forced it using a sawtooth function. And that sawtooth function is shown here. What we do is we start off with a large negative force that gradually weakens, is zero for a moment, and then we start pulling. So it's a strong push, and then weaker push, and then pull, 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 and then instantly jump to a push. So it's a bit irregular. It doesn't happen that often or quite that cleanly in physical systems, but it often happens in electronic systems. The key thing about this function for our purposes is that we have a period of 4, which is going to match what our system has, and we also have an on and off, or a positive and negative contribution, roughly half on each side. So what we expect is when the mass is moving downwards, eventually we're going to get in sync so that we're pulling when the mass is moving downwards and we're pushing upwards when the mass is moving upwards. To be able to see that mathematically, though, we need to write out our function in a little more mathematical notation rather than just the graph. What we have here is a function that's straight line, and if we check out the slope, it's actually slope 1. So on the first interval, we simply have t minus 2, and that applies all the way up to t equals 4. Then when we jump down to the next function, we can imagine where the intercept of that would be, or we can imagine as a shifted version. So it's t minus 2, but it's been shifted to the right by 4, which is a minus 4 in the notation. And that would apply up to t equals 8. If you wanted to, you could actually break that out and write it as t minus 6, which is where the intercept would be if we continued down here. But as it turns out, this form here is going to be more handy when it comes to handling Laplace transforms. It also gives us a nice pattern to work with here. On the interval from 8 to 12, we'll have t minus 8, and so on. The start of the interval marks the shift that we're going to need. To write the saw function using step functions, we can simply note that on the interval from 0 to 4, we had t minus 2. So we'd have t minus 2 times u0 minus u4. Plus the function that applied on the second interval from 4 to 8, and that was t minus 4 minus 2. That has a u4 minus a u8. And then we just keep going. We would have a t minus 8 minus another 2 times u8 minus u12, and so on. Last but not least, it'll help us in advance if we compute the Laplace transform of all of this. So we remind ourselves that the forward Laplace transform of u sub a times f of t is the exponential e to the minus as times the Laplace transform of f of t plus a. So whatever the step function is, we shift with a plus a. What does that mean for us here? Well, we have our saw function. I'll write it as saw up here as well for clarity. Its transform, when we have the u0 term, nothing is affected. So we simply have the transform of t minus 2. And that's 1 over s squared minus 2 over s. Then we have the negative u4. So we'll have negative e to the negative 4s. For u0, I left off the e to the negative 0s. It's just a 1. But for the u4, it's going to be handy. However, we have the transform of that of t plus 4 minus 2. So we'll come back to that. We can now proceed, but it'll be helpful to simplify before we take the next step. The reason being we have duplication of the u4, u8, and so on, and we're going to get some cancellation that we can take advantage of. So our f saw can be rewritten. u0, all we have is t minus 2. And in fact, u0 is the same thing as 1 because we're only considering times that are positive. If we add the u4 terms, we have a negative sign here, so we'll have a negative t and a plus 2 for this. And then when we go over to the u4 here, it's positive. So we'll have a plus t minus 4 minus 2. And let's just consider the pattern we see for the other terms. u8 will have a minus t minus 4, or plus 4 rather, plus 2, and then we'll have a plus t minus 8 minus 2. Now what do these terms simplify down to? We end up with a plus 2 and a minus 2 canceling, plus 2 and a minus 2 canceling. We have the t's canceling, and we're left with a negative 4. Also, when we have the negative t and plus t, those cancel, and lo and behold, we end up with a negative 4. And if you went to the next term, you would find a whole bunch of things that simplify down to a negative 4. Well, that's not so bad at all. We have a leading term that we need to transform, and then we're going to have all these other step functions, u4 and u8 and u12 and u16. All of those together simply times negative 4. So that makes our transform very straightforward. The Laplace transform of our forcing function here is going to be 1 over s squared minus 4 over s, except it's going to be negative 2. Careful, this 2 here was miscopied. That should be a 2 there. And so it's a 2 here as well. That's this transform here. And then on the next step, let's actually bring the negative 4 out front. So negative 4 over s times e to the negative 4s plus e to the negative 8s plus e to the negative 12s, and so on, because the transform of a u times a constant is just the exponential over the s function. And so that gives us quite a nice, simple, straightforward transform for this sawtooth function. Our next step is going to be to see how this affects the solution to the actual differential equation. How does the spring respond when we apply this sawtooth force function?